In class today, we talked about the mean value theorem and two of its corollaries. So what I want to do in this video is just summarize what we discussed in class and then also run through some examples of what we can do with the mean value theorem and in particular with corollary 2. So essentially what the mean value theorem says is if we have a continuous function on a closed interval and that it's differentiable on the open interval, then there's at least one point C in the open interval where this equation holds. And we drew a little picture of this in class, but essentially what we're saying is if you have a function and it's defined on a, b, so let's say it's this piece of the function, then the slope between a and b, which is f of b minus f of a over b minus a, is equal to the slope of the tangent line for some point C in between. So based on my picture, that looks like it might be about here, and this is a tangent line coming through here, and those, the blue and the red, are parallel. So the derivative at point C, which is the slope of the tangent, is equal to the slope of the secant connecting a comma f of a and b comma f of b. So that's the mean value theorem. And it's an interesting theorem in and of itself, and I have a separate video where I do the proofs for the mean value theorem and the two corollaries. But in particular, what we're really interested in for the work that we need to do is corollary 2. I will say a little bit about corollary 1 before I get to corollary 2, though. Corollary 1 is basically telling us if our function is differentiable over interval I and the function is 0, the derivative of the function is 0 everywhere in I. So as long as we have a point in our interval, if the derivative is 0 everywhere, then this thing has to be a constant function. If the derivative is 0 everywhere in the interval, the function must be constant. It's telling us what we kind of already know, right? That the derivative of a constant is 0, and we're just saying if we work our way backwards, if we know the derivative is 0 on a particular interval, then that function has to be constant on that interval. But this second corollary is really the one that ties in what we need, that introduces what we need to start talking about antiderivatives and integration. So in particular, this time we're talking about two functions, f and g. And if their derivatives are the same, then those functions differ by a constant. We call that constant capital C. So I want to say a little bit about capital C because earlier we talked about lowercase c in the mean value theorem. Lowercase c, which is this x coordinate somewhere in the middle of the interval AB, has absolutely nothing to do with capital C. Capital C is a big deal, but for different reasons. And it's unfortunate that in the same lesson we're going to talk about the plus c, capital C, and also have you locate the lowercase c, which is the point that the mean value theorem is telling us exists, right? Mean value theorem is essentially an existence theorem. Okay. All right, so I want to show you these things in action. We'll come back to this corollary 2 in a second when we do the examples. But first, we'll go ahead and attack an example of solving a problem to find lowercase c using the mean value theorem. But the rest of what we do will have to do with this plus c. Okay. So the first type of problem that we're going to want to solve, you're going to be asked to solve, I don't know if you want to or not, but let's assume you want to, is going to be basically applying the mean value theorem so that we can find the point C, which the mean value theorem guarantees exist. So we have a continuous function here. F of x is x squared plus 2x minus 1, and we're on the closed interval 0, 1. And what we're saying is that somewhere between 0 and 1, there is an x coordinate, which we'll call C, that has the value of the derivative, the slope of the tangent line there, is the same as the slope of the secant connecting the endpoints. So here's how we attack this thing. First of all, let's go ahead and get the derivative. So f prime of x, that's going to be 2x plus 2. And then remember that our formula called for f prime of c. So let's go ahead and see what that looks like. You literally put the letter c into the derivative. So f prime of c is just going to be 2c plus 2. I'm just skipping over that so I can change it to red. So f prime of c is 2c plus 2. And then what we'll do is we'll plug this f prime of c. Remember the formula for the mean value theorem was f prime of c equals f of b minus f of a over b minus a. So I'm going to write down 2c plus 2, that's my f prime of c, equals, and I'm going to calculate these 4 values. Well, 2 of the values I have to calculate. 2 of them are given. So f of b happens when you plug 1 into our function. So f of 1 is going to be 1 plus 2, which is 3 minus 1, which is 2. And f of 0 is 0 plus 0 minus 1, which is negative 1. So 2 minus negative 1 in the numerator. And then in the denominator, it's just going to be 1 minus 0, because b minus a. So I have 2c plus 2 equals 3 over 1, which is 3. And then I just solve for c. So I do minus 2 on both sides. You guys know how this goes. A little bit of algebra 1 there. And I end up with 2c equals 1. So c equals 1/2. Okay, so what have we found? Well, what we've done is we've found the x-coordinate for the point c, c comma f of c. We found the x-coordinate where the slope of the tangent line, f prime of c, f prime of 1/2, is the same as the slope of the secant that connects the two endpoints. In a sense, we just found c. In essence, my goodness. I'm not doing another take on this video, so you're stuck with this. But that's our job, was to find c. This is lowercase c, and we did that using the mean value theorem. You'll be practicing a few of these when you do the exercises. I'm stumbling through this one, so let me see if I can do a better job on our next example. So as I mentioned, I've got these written wrong, so let me finish these off. These are all f prime. Sorry, way to go. As I mentioned, that corollary 2 is a big deal for us. It tells us that functions that have the same derivative differ by a constant. So many of the problems that you work on tonight are going to ask you to find all the possible functions with the given derivative. So I've given you some derivatives here, and we want to find all the possible functions that have that derivative. So this works in 2 parts. The first part you're going to do is you're going to work on the expression they gave us, and we're going to work backwards to figure out what the function was right before we took the derivative. This process is called finding the antiderivative. Eventually we'll call it indefinite integration. But for now, we'll just call it working backwards. So I hope you can imagine that if we have a derivative that's 2x, the original function had to be x squared, right? We know that the derivative of x squared is 2x, so if I'm working backwards, the original function f must have been x squared. But because the directions are telling me to find all the possible functions, what we have to do is consider all those functions, and corollary 2 tells us that they differ by a constant. Now, we don't know which constant it is, but in our corollary, we use that plus c to represent that constant. And when we want to represent all possible functions for problems like this, when we're all done, we stick a plus c on the end. This is a capital C. It's different than that lowercase c from the mean value theorem. The lowercase c is a variable that has one real number value. In that last problem, c equaled 1/2. In these problems, when we're representing all possible functions, this c right here, this plus c, is a magical creature. It contains all of the real numbers. And that's how we're able to express an infinite number of functions that all differ by a constant. Essentially, these are just vertical shifts of the parabola x squared, but the point is that in order to represent all possible functions, we stick this plus c on the end, and it represents all the real numbers that could be there, not just one particular real number. And once you get the hang of this, then it's just a matter of working backwards each time. So I can play the same game with this derivative, f prime of x equals 2x minus 1. I already worked backwards on a 2x. That was an x squared, right? The derivative of x squared is 2x. Then I have to think about what expression has a derivative of negative 1. And it turns out, after a little bit of thinking, that I remember that's just a negative x. So the derivative of x squared is 2x. The derivative of negative x is negative 1. But remember, we're looking for all possible functions, and they all differ by a constant. So we stick a big old huge capital plus c on the end of this thing, and that takes care of all possible functions. And then now, once you get the hang of it there, it's just a matter of cranking out all these, what we call antiderivatives of each of these terms. We're just working backwards from each term. So when I take the derivative of x cubed, I get 3x squared. I already did a derivative, the function that has a derivative of 2x, which was x squared. I already did the minus 1, that was a minus x. And then we don't forget the plus c because we're finding all possible functions. In the next lesson, we're going to formalize this language of working backwards into something called antiderivatives, and there's a whole set of notation that goes along with what we call indefinite integrals. But for now, we're going to just use this loose definition of this idea that we're working backwards to figure out what function produced these derivatives. Okay, and then of course, don't forget the plus c. That's kind of a big deal. Let me show you an application and we'll get this video done. Once you get the hang of this idea of working backwards, there's two kinds of applications that we're going to solve. The first is without context, but related to the second one. And these are called initial value problems. So what's going to happen is you're going to be given a derivative and a particular point that we want our function to go through. So we are not finding all possible functions. We are finding the one function that happens to go through the origin and has this derivative. In essence, we are trying to find the plus c, the capital C. We're trying to find the capital C. That's what we're doing, okay? Which is different than finding the little c from the mean value theorem. So here's how this works. We start out the same way we did in the last problem. We find all possible functions. We already did that for 2x minus 1. That was x squared minus x plus c. And then we use this initial condition, right, the point 0, 0. We use that to solve for capital C. And here's how that works. This spot right here is an x-coordinate, and this spot right here is a function value, a y value. So I'm going to put the y value where the f of x is in the equation, and I'm going to put the x value where the x is in the equation. Now, these are all zeros, so it's going to be kind of an easy calculation to figure out what plus c is, but essentially you fill in the function value and any of the x's, and then you solve for c. In this case, we get c equals 0. And now that we know c is 0, we know that the function that goes through 0, 0 and has the derivative 2x minus 1 is this f of x. It's just x squared minus x. That is the only function that goes through the origin that has this derivative. So these problems have one answer, not an infinite number of answers. And we don't end up with a plus c on the end. We use the initial condition to figure out which c we're talking about. That's called initial value problem. We also are going to add a little context to these problems. We're going to use an application from physics. I think you'll remember that we worked with position, velocity, and acceleration. So here's how we use this corollary to the mean value theorem to solve those initial value problems. Let's take a look. So this is essentially the same type of problem as the one we just saw in the last example. The difference is we've added this context from physics. we're now talking about finding a body's position. I got to slow down and spit this out here. We are now talking about finding a body's position given an initial position and its velocity at time t. So in other words, we're given a derivative here, right? Velocity is a derivative, and we're told where this point started, this particle started. And essentially this is an ordered pair. This is just 0, 10, and this thing is just f prime, right? So the goal is the same. We're going to work backwards from 9.8 t squared plus, or t plus 5. We're going to come up with all possible position functions, and then we'll use this initial condition to find the one that we're interested in. So instead of writing f of x here, we're going to put s of t, because that's the function we're trying to find. That's the name of the original function, the position function. It takes a little thinking, but in the same way that we went backwards from 2x and ended up with x squared, we can work backwards from 9.8t, and I think you'll agree that the function that has that derivative, the expression that has that derivative, is 4.9t squared. And if you're not sure, you can check this. The derivative of 4.9t squared is 4.9 times 2 times t, and that is 9.8t. And then for the term 5, the expression that has the derivative of 5 is just 5t. But don't forget, we've got this plus capital C on the end. And our job is to figure out what the value of C is that meets this initial condition of 0, 10. So now we do what we did in the last problem. I'll put 10 in for the function value. So 10 goes here. And I'll put 0 in for the t values. Apparently my zeros are red this time. And then I'll just solve for c. So this is 0, and we end up with c equals 10. So the position function that has the velocity of 9.8t plus 5 and an initial position of 10 is s of t equals 4.9t squared plus 5t plus 10. That is our position function that meets this criteria. So we're moving into a whole new branch of calculus here. These are the building blocks to what we're going to spend most of the semester doing. But for today, make sure you can solve for lowercase c using the actual mean value theorem. And then make sure you can find all possible functions using corollary 2, working backwards from derivatives, and then also using that process of working backwards, which we call antiderivatives, to solve some initial value problems. The problems might have context, like this one, or they might just be abstract, like the previous example. Okay, that was a summary of what we did today. If you have any questions, you know where to find me. In the meantime, take care.